All right. Hi, everybody at home and here. So I'll introduce Andy. I'll just say, though, just a bit more. You have the course schedule. Andy will speak about this more. But thinking now of my introduction for Andy, I realize that basically your lecturing staff involves a mathematician, just departed yesterday, a physicist. Everybody here is implied mathematician and a computer scientist, a physicist. Paul Verbeek, a computer scientist, and then myself, a statistician, really. I mean, I think if we have to divide it this way. So the physicist, Andy, Dr. Andy Ferris, has a PhD in physics and has done multiple postdocs around the world. Spain,
yeah,
Canada.
Yeah, and a little bit at UQ.
And at UQ.
Yeah.
And is actually a very good mate of Paul Bellet that left yesterday. They're really responsible, together with a few other people, for introducing Julia into the Brisbane environment, I would say. At least that's what I believe. And Andy actually contributed quite a lot to the Julia ecosystem. So a lot of packages that are used in Julia throughout the world, Andy contributed to that. So I'm sure that you'll hear from him on open source contributions and such. So
yeah,
you have the pleasure of now having Andy for one unit, then we part, and then we'll meet him again.
Yes.
All right. Enjoy.
Well, thanks, Yoni. All right. Thanks, Yoni, for having me here again. This is the second year I've been involved in this course. Yoni has been looking forward to creating a course like this for a few years, and we spent some time beforehand with a group of other people, including, I think you met Amy and Anna and Paul and so on, creating this course for beginning last year. So it's good to be back. We're shaking things up a bit this year. So I'm going to teach a section called Unit 4. Okay. So Unit 4, it doesn't directly have like assessment attached to it per se, but it's really going into more of the fundamentals of how Julia works and how you can use it and get your best effort out of it. Okay. So that's where we're going. So before I jump into that, maybe I'll just say a few words about my background, as Yoni did. I think, as Yoni said, I've done a PhD here at UQ, over in the building just over there, in the physics building. I did this doing computer simulations of Bose-Einstein condensates. Okay, so I used to fire up programs, and would probably have to like write a bunch of MATLAB code or something and try and run a simulation that sort of matches experiments that were being done at the time and this kind of thing. And we'd either use MATLAB or we'd use a programming language like C. Okay. And so like, why were we using MATLAB and C? Well, MATLAB was a nice language because you could just easily do mathematics with it. You could have arrays full of numbers. You could do like solve differential equations in it and do different things in it relatively easily without too much code. But what could happen back then, and it's improved since then, is that when your code gets more complicated, it could actually run a bit slower than would be optimal. Okay. And so because we were doing research and we're trying to solve problems that hadn't been solved before, we'd often go and rewrite it in C. Okay. So we'd take this code we'd written and we'd rewrite again in C, and we'd have to kind of like make it run faster so we can do like a bigger simulation that lasts longer or is more accurate. Paul Bellet spoke to you a lot about like choosing a time step for solving, integrating or solving a differential equation, using different methods for solving differential equations and things. So it's definitely all evolved in that kind of thing during my PhD. After that, I did some more postdoctoral research. If you remember yesterday's lecture, Paul talking about the SVD, and like compressing images. We were doing a similar technique, but trying to compress quantum states. So if you look at a quantum wave function and you're trying to study something like quantum computers or something that involves a lot of quantum components and a lot of entanglement, then what you get in quantum mechanics is the state space that you need to represent your quantum state grows exponentially with the number of things involved. So if you think of a quantum computer with qubits, you need like 2 to the power of number of qubits of like numbers to represent of complex numbers to represent the state of your of your quantum computer at any instant in time, right? And so when if 2 to the power of n, as you know, like 2 to the power of 32 is like 4 billion, and like 2 to the power of 64 is like some number that's astronomical and could never like store in a computer. So what we'd do is instead of like trying to solve and store entire states, we'd like come up with approximations, which like that SVD that Paul was saying, is like you cut off some tails of some things using linear algebra, and you just sort of discard them because the coefficients or whatever, like the weight of those bits in the tails was astronomically small. Okay, so you could actually, in some cases, you'd solve things almost perfectly accurate to floating point precision. That was fine. In other cases, it's more challenging. You couldn't. You'd have to try and mix and match a bit with Monte Carlo or other methods to try and get something out of this. So that's the kind of research I was doing after my PhD. I went and did a postdoc in Quebec, and then I went and did another postdoc in Catalonia. So everywhere I seem to go wants to separate and be a different country. I'm not sure why. Had a few children along the way in different continents, so that's a lot of fun. And then came back to Brisbane. And when I returned back to Brisbane, I came back to a job with a friend I did my PhD with, but also with Paul Billette. Okay, so we used to work on geospatial data at Fugro, and we used to they would have planes and they would capture lots and lots of data using imagery, LiDAR, and they would have GPS and other sensors, inertial measurement units and things on the airplanes. And we'd have to do a lot of maths to like figure out, A, where is the airplane? Like B, which direction was the camera or the LiDAR pointing? And like C, like if a LiDAR is like a laser machine, it shoots like a little laser beam out, and it hits a target like a tree or the ground or something, and it bounces light back. And light doesn't go infinitely fast; it only goes at a measly 300,000 kilometers per second. So if you just kind of like measure those nanoseconds and divide by 300,000 kilometers per second, you can actually figure out how far away the thing that reflected back was. And so knowing where the plane is and where it's pointing and like how many nanoseconds that took, you could actually figure out where stuff is in the real world, make a 3D map. Okay. And so like, for example, one of the products like that spun out of a product the Queensland government, I suppose, owned it for Ergon or Energy Queensland now, for finding where the power lines are, which trees are touching the power lines, and trying to cut the trees so you don't have fires, which poles are falling over or leaning too much, and this kind of thing, which wires are too low. But there were lots of things you can do in the geospatial space. It's really fascinating space. And again, one of the things you find in those kind of spaces is you have a lot of data, and you need to crunch all that data, and you need to find insights about, say, the real physical world in that case. And again, you have this dual problem where you're trying to solve something that people haven't really solved before. Right? Like LiDARs aren't brand new, but like the idea of like making 3D maps of like the entirety of Queensland is kind of a newish concept that you wouldn't be able to think about doing, 20 years ago. So you're actually having to do a lot of kind of research kind of work, thinking about how to go and find things. Like if you just have dots in 3D space, and you want to turn that into like, where's the ground? Where are the power poles? Where are the trees? Like you actually have to do a lot of work and have a lot of interesting algorithms that like find power poles. Like a human could probably go around because you have a lot of context about like the shape of streets, and you know that power poles are near streets. But if you're in the middle of a farm and you see a few dots, they could just be random noise, there could be nothing. So like you kind of have to like design your algorithms very carefully, kind of deal with that. And so that's like an interesting research problem. But on top of that, you're getting like a petabyte of data every year. So does anyone know what petabyte means? So it's like 1,024 terabytes. Okay. So, and then like a whole hard drive is like a terabyte, right? So, and like there was a mini industry in like literally mailing around hard drives from the plane where the planes were scanning to back to the base to upload to the cloud, like Amazon AWS cloud, right? And so one of the cost saving measures is like some ridiculous numbers of thousands of dollars are saved by moving to a slightly smaller hard disk that weighed less and the postage was less, right? So like, it's interesting when you're talking about data at scale, is like, even the physical part of that can be challenging. But once you have it on a, let's say a cloud, AWS cloud on their S3, which is like an infinite size hard drive, semi-infinite size hard drive, then you got to process it. And like that takes time and that takes money. And there's only so many computers, even in the cloud. And there's only so much money you can make before you go spend before you go bankrupt. So you have this problem is you're trying to do something that's really hard and you want your programs to run as fast as possible. Okay, so you're trying to solve these really hard problems from a mathematical perspective, like statistics and machine learning, physics, all these things are coming into that, right? And like these companies are employing PhDs and you know, graduates, master students, all these kind of people to solve those problems. But then once they're solved, they need to run them at scale. They need to run them fast without any overhead. So there has to be a degree of, you know, efficiency and mechanical sympathy and like all those things that your program is really getting the most out of the machine you're paying for, just so you can get your work finished in time. Yeah, since then, I've moved on to another company, which is a bit more business focused. We work on simulating businesses. It's a lot of fun, and that's probably a little bit more tied back to unit is it unit 7, and I'll speak more about that then, really. But so basically, I just wanted to give that introduction. Because I think it's good to kind of, one thing I really love about Yoni's idea for this course is having people from different backgrounds give you some perspectives and share some of their experiences, right? And you've got the guest lecturers and you've got Paul and Yoni. So like my perspective on all this, and one of the reasons why I use Julia is you kind of want to, if you want to solve real life problems that are hard, you've kind of got a few things that you need to worry about, okay? So if you have and I'm just going to talk about a programming language now, because Unit 4 is all more about the Julia programming language and like how to get the most out of it. So I'll just talk about like the programming language side of things for a sec. So you want your programming language, if you're solving these kind of problems, like execution speed can be a problem, right? So whatever problem you're trying to solve, you hope the environment you're solving it in, you know, the software you're using to solve it, the programming language and packages and libraries and all these things, will solve it fast enough to be practical for whatever problem that you have at hand, right? You'd want to be able to like solve, like as the programmer, as the person going and solving this problem, like you might be good at writing things on pen and paper, say, and figuring out what you want to do. Like how long does it actually take you to write that into code, right? How hard is it to take your idea in your head and bang it out even at the REPL for Julia, right? Like how long does it take you to kind of like create something that does something? And some programming languages, this is quick and sometimes it's a bit slow, and it really depends on the focus of the language. And the third thing, which is really probably not very obvious to people in like undergraduate, that you will gradually understand as probably being the most important out of all these is how this all evolves as your software gets more complex. Okay, so all these problems I'm solving, the startup I'm working at now, the research I used to do, the work with the LiDAR, like they involved like more than one person, right? Like research teams or like entire almost divisions of a company working together, trying to create like a large piece of software that has many components that interact and that do many different things to just sort of like deliver the value that they're trying to deliver at the end of the day. Okay, so what you want is that, let's say it's really easy to bash out a really quick program. Sometimes it can be really hard to kind of like share that with other people and have two people editing it, you know, maybe even simultaneously, which is one thing we use Git for, is it helps deal with people working at the same time. And what often happens, and this should really be thought of kind of like the default mode of things, the default mode of things is that this gets harder and harder and harder over time. As your program gets more complicated, as you add more features, let's say you add one feature and you add two features, you add three features, you add four features. Like the complexity around your software tends to go like more or less exponentially. Like it grows really, really fast. And certainly not linearly, right? By default. So you have to kind of like take a step back and think about how to make things modular so they actually plug and play like Lego bricks a bit more, rather than like sticky tar. Like you don't like it's what's going to glue together. It'll be like a bowl of spaghetti bolognese, and like you can't really edit it because you pull this thread and like the spaghetti over there moves. And so you often see what programmers to write as spaghetti code, right? And this is like someone's given you a job and you're like, I want you to take this program and make it so when the person clicks the button here, this thing comes up over there. And you're like, okay, that sounds pretty easy. And you go in and you like change one thing, and then all of a sudden three other things are broken, right? Because you edit one thing and everything else breaks. So and what happens in a software team or product that lasts a number of years, or even a research project that has like multiple PhD students or something coming and going, is there's more than one person involved, right? So what happens is one person might create it and they might leave, and then another person comes in, they might have to improve it and then leave. Okay, and so one of the corollaries of this like team environment, this scalable engineering, is that software is always read more times than it's written. Okay, so if I write a line of code in my job, I'd probably expect to come back and read it myself after I've forgotten all about it in a few months. Maybe in 3 months, I've forgotten that code almost completely. I mean, I might have some idea of what I was trying to do, but not like how those particular lines of code function. But also other people on my team will have to read it. And if I leave, or I've left previous jobs, other people have to sort of maintain that code. If there's a bug, they have to find it. If they want to add a feature, they have to go edit it. If they want to re-implement it from scratch, it's like chess and fence. They're probably going to have to read it, understand what it did to figure out why it was doing those things. And some of them are just batshit crazy ideas I came up with, and some of them are real reasons, like real business constraints, that there's something weird in the code. Like to kind of figure out which is which. So you want to kind of like make code which is easy to read, and like maybe add some comments to explain why certain things are happening and things like that. Okay. So what drew me towards Julia is coming from sort of languages like C and MATLAB. It was really solving all these problems simultaneously. I didn't have to use multiple programming languages to solve a single problem. I could like use Julia. It runs fast if you use it well. If you know like about packages and like how to do different things, it can be really easy to solve mathematical problems. That's number two. And also it has this sort of concept of, has types and interfaces and things. So it can be possible, or it's certainly a lot easier than something like MATLAB, for example, to create code which is sort of easy to share and reuse and these kind of things, and more like Lego plug and play. But it's not like the only programming language in the world. There's like Python and Rust and Java and Go, and there's many languages out there. And they all look at these three problems. And since programming languages existed, since people moved away from writing assembly on punch cards, since then, people creating programming languages realize people want pretty much these three things. And in a commercial environment, generally we've probably moved to a point where computers are cheap and people are expensive. Okay, so it used to be you'd have one mainframe computer and it would take up a whole building, and you have a team of 20 programmers, and they'd all have PhDs, and you'd pay them all big bucks to sit there and program the one machine for 10 years, right? Nowadays, it's more the other way around. On one computer, I launch my things in the cloud. There's probably like 100 computers per programmer, right? So the computers are cheap and the people are expensive, and you're trying to solve more and more complicated problems because computers are faster, they can handle more complicated problems now. So while back in the day, people used to eke out execution speed by writing assembly and stuff. Now kind of the order of priorities has flipped. Usually the third one's more important than the second one. The second one's more important than the first one. But you still need to satisfy all these to the extent that's required. Now, different languages have different requirements. Let's look at number two, all right? Coding speed. So does anyone have an idea of a language which idea of a language which prioritizes number 2 over other kind of things it might care about? Yeah. Scratch. Okay. Yes. Okay. Scratch. Yeah. Okay. That's a cool answer. I got it. There's another answer. Paul's been speaking to you about. Yeah. Yeah. Sorry. Python to some extent. Yes. Yeah. Yeah. They've tried to add types and things to make it more scalable and so on. So it's definitely, but it is definitely like that. It's definitely some Scratch and Python were both designed as languages easy to learn, easy to get into as sort of their primary feature. But here's one here. Anyone know what this is? All right, like, you know, right? I can go like, here's a bash program, right? It's kind of incomprehensible to create things like this. It's very easy to make errors in any of these for loops and syntax errors. You don't know the types of things. You don't really have, you know, compound data structures. You know, the idea of an array in bash is like strings with spaces in between. So bash is a language which is really focused on letting me do something really fast, but it's sort of hard to do scripts and write complex software in bash, right? And also it's not really designed to run fast. So that's just me trying to point out like there's different trade-offs here and they're all legitimate trade-offs. Like if you're using Rust or C or C++, you know, you're probably wanting to write code very close to the middle, prioritizing execution speed, probably correctness, hopefully, and this kind of thing while you're writing, you know, maybe operating systems, like drivers or like databases and these kind of things. Okay, so that's the general thing, and sort of like just wanted to speak a little bit about my experience and how this relates. So Julia is like a high performance language and it's designed for solving mathematical problems primarily, but it's also a general purpose language. Okay. And so the code it compiles does run close to the metal. It makes proper machine code that's sort of compiled down like a C program would be. And it makes a lot of affordances so that you can like solve your maths problems really quickly, right? So, but what I really want to get to in Unit 4 is more the third point, is that it sort of also does this in a way which is scalable, okay? That you can have code, you can come back to it and read it and edit it and stuff. So what I'm aiming to get out of Unit 4 here is how to use Julia to the best effect so that you're not like, you know, we'll talk about how to make it run fast and different things like that. But mostly like how do you use it in a way so that, you know, you can come back to your code and you can edit it, it makes sense, and the people grading your code can read it and understand it, and this kind of thing. Okay, so that's where I'd really like to get to. And we've got maybe 3 or 4 hours of this kind of thing. Okay, we'll get cracking. Is there any questions before I get cracking proper? Online. Don't know how many of you online. I hope you can hear me. All right. So what I want to focus on in this lecture is more or less go into some more details about the syntax of Julia, just so that when we get into more complicated things and you're doing stuff with Paul Verbeek, that there's no confusion about like the surface syntax or like something which is just like, why is it written that way? And Julia has quite a little, quite an interesting amount of syntax. So we'll just go through for the next, let's say half an hour-ish, and just fly through like some details about Julia syntax. So in Julia, the first rule is everything in Julia is an expression. Okay. In some programming languages, this isn't true. So in Julia, if you have something and it's syntactically valid and you can run it, it will always return a value. If it can't run it, it'll throw an exception, right? So they're the only 2 real things. If it's syntactically valid, you get one of those 2 things. So for example, an expression 1 + 1, it's a piece of syntax, right? It's sort of a string with 5 characters, but in this case, you could also think of it as sort of an expression where plus is operating on 1 and 1. And that returns a value. this case the value is 2, right? That's pretty simple. So one of the interesting things about Julia, which you can't probably do in, say, C or JavaScript or other languages, is like even things like an if statement. Well, it's not even an if statement, it's an if expression in Julia. So in most languages, an if block is there to sort of like tell the CPU to actually, physically perform an action in this branch and physically perform an action in this branch. We're taking more of a functional or like a mathematical approach, whereas like if you go this way, you get back this value. If you go back this way, you get that value. Okay. So in Julia, you can say like, is x even equals if x modulo, has everyone seen this modulo one before? If x modulo 2 is 0, okay, then it's an even number, right? Or it's an odd number. Okay, so like this variable gets corresponding to that value there because x is 42 and 42 is even. And like many languages, Julia has like this ternary operator, which ternary means 3, like taking 3 inputs in this case, with a question mark and a colon. So x is even, so this is a shorter way of writing all that. Okay, so it's a lot less typing. It's a lot more concise. But it's worth noting these are 100% compatible. The first thing Julia does is read text you give it and like converts them both to the same kind of data structure internally. Like that's like step 0 for it. And then it starts compiling it and everything. So this is what we call syntax sugar. Okay. Oh, yes, have you got a question? Yeah, okay. So we can do this at the REPL. Okay. So I'll go Julia, and we can answer that question. So if I just type 42, right? I get that, right? If I go x equals 42, I get 42. Okay. So, and this is really interesting in Julia. You can actually chain these together, right? Chain, right? You can go like x is 10, y is 10. And because everything's an expression, even assigning a variable, a value to a variable, finding a value to a variable, even that is an expression in Julia, which is the right-hand side of the equal sign, right? And if you think about the way this one works, clearly it's evaluating right to left. That makes sense, right? Like, because it's not saying x equals y and then doing equals 10, because that would have exploded. Yeah, that's a good question. That's a really good question. Yeah, so syntax sugar. So that's something to make your program's life a bit sweeter. It's just surface level syntax that sort of like a trivial transformation of your code. I say trivial, like it could actually be quite a large transformation that would like involve a lot of typing, for example, to make such a transformation with syntax sugar. But in some sense, it's just something else you can do already, but written a different way. So it's not a new feature of the underlying language, the underlying language semantics right at the bottom. It's just like a different way of writing your text. That's what syntax sugar means. Julia has blocks of code. You've obviously seen functions before, but like you can use begin and end to create a block of code whenever. And the rule is in Julia, the last expression of the block of code is the thing that's returned. So this block returns 3, right? Potentially line 1 and 2 would have like assigned things to variables or mutated an array or something. So maybe they're not useless. But in this particular case, if they're kind of like just pure expressions that don't have any side effects or assign any variables, they kind of like get discarded. They're not really important. They don't do anything, that 1 and 2. Okay. And you see blocks of code everywhere. Like you see them in functions, you see them in loops, you see them in if statements and things like that, right? So in most blocks don't require a begin. Like things like function implicitly begin a block and you have to end them, right? We often use indentation, or almost always we're using indentation to sort of like indicate visually to the person who wants to read the code which block you're in. Like where does the block start and end? I can tell this block of code starts and ends here just by realizing that there's this gap here, right? And every modern language has braces, or like Python has white space and indentation. And like you'll see this is like a generic thing you'll see everywhere. And then this while loop has a block in here which starts here and ends there. Okay. And then this if statement has like an if for the positive branch and like an else block for the negative branch. Yeah, cool. So an interesting factoid that I should tell you is that if you have a while loop or a for loop, they always return nothing. So that's an expression. If I put x equals while blah 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 blah, all I'm going to get back is this thing called nothing. And we'll talk about nothing in a minute, but nothing is a value. We'll talk about it here. Yeah. So if you have an empty block of code, say, this just returns nothing. Now this program we're using, Weave, and the REPL sort of hides nothing from you. Like it's like, oh, it doesn't even print it, right? But like there's this function called dump, which sort of tells you whatever things are. You can go type of nothing. And this is an actual value in Julia. But the thing is, it's a 0-byte value. So there's no real data associated with it. When the compiler realizes there's nothing there, it can kind of like basically ignore it and skip over it. So it's just like there's kind of things the compiler can do to make sure your CPU is not wasting time and is actually solving the problem you want to solve rather than like dealing with weird bits of the language semantics, right? So, that's a bit contrived, begin end. You'd never really write that, right? That's not very useful. But like you might have an if statement, and often you'd like, okay, oh, if this is true, then do something else. And there's no else branch, right? It's just, you just care about it being true. You don't care about it being false. So what happens if, there is no else statement, and you want to assign something to it? Well, it's kind of like there was an else branch, but there's nothing in it. And it's sort of an empty block. And the rule is an empty block returns nothing. Okay. So this code is pretty much equivalent to that code. This code is very much equivalent to that code. And again, this is just surface syntax sugar, right? Like the compiler will implicitly sort of create these kind of things for you during the first thing it does when it sees your code. All right. Often functions which are designed to not compute something or return a value, they're designed to do something like print line or whatever. What they're going to do is return nothing as well. Okay. So does anyone know what you'd call that in C? You have a function that's designed to do something rather than compute a value. Like what's the return type of such a function in C? Yeah, void. That's right. So C has a void type, and in C there can be no value type void. You can't assign void to something, and like this goes together with the semantics that think not everything is a statement, not everything is an expression. You can't in C necessarily write, or C++, you can't write like auto x equals f of brackets, right? You can't just do that because it might return void, which basically means it doesn't return something you can assign to variable, which means you'll throw an error. Okay. At compile time. Yeah, so why is Julia like this? Why is it just follow the tradition of other languages that don't have this idea of everything as expressions? And this idea of everything being expression comes from Lisp, which was very famous for metaprogramming. So a metaprogram is a program that creates a computer program. It's very meta. So what you can do in a language with metaprogramming, well, at least there's multiple sort of types of metaprogramming. We're talking right now about syntactical kind of metaprogramming, is that you can use macros and so on to like translate your code from, one kind of type of expression to another kind of expression. And you can do that with a computer program. Now it's trivial to do this as text. Like you can take your source code as text, and then you could like spit out other text. And this is what the C preprocessor does. And that's sort of terrible. But if you really want to do a good job at like processing text, the first thing you're going to do is write a parser for the code. So what Julia does, generally with macros and things, it'll pass the code, put it into what's called a syntax tree. So it's like a data structure that contains the syntax. If you want to see a syntax tree, we can sort of see it here. This is like the expression 1 + 2. And if I just go dump on that, you can kind of see that it's an expression. It's the type or the head of the expression it's a call expression. You're calling plus with 1 and 2. right? So it kind of creates this, and it is going to be a nested data structure, right? Like then it could be like, sorry, my keyboard's a bit screwed. It can get nested in things as you kind of like have things inside other things. And it's going to be nested if you have blocks inside of if statements, inside of while loops, inside of functions, and everything's going to get nested. Okay. And so the whole purpose of everything being expression and all this is it's actually kind of valid to replace one expression with another expression. And that's what a macro does in Julia. So you've probably seen at show. I don't know if there are any other macros that we've seen that are useful. Probably there are ones like you can see like which. This one tells you where's the line of code that defines this thing. And this is my all-time favorite macro in Julia, edit. Has anyone seen edit before? What do you think it does? Yeah, so I've got Vim set up as my editor. That's my environment variable in Unix. And it's actually taken me this line of code. There's this internal function here in Julia called add in. And that eventually corresponds to some kind of like machine code instruction for that data type, right? So not only can I see like my own code with edit, but I can see the Julia standard library with and compiler and like the bits of the compiler that are in Julia things I can see in that way. So I think that's a bit of fun at edit. Because you know, obviously in Julia you can overload plus and overload things with different methods. It's often confusing which one it is. So, all right. So that's just like surface level syntax and that kind of metaprogramming. But like I was just mentioning, like Julia has all these types and methods that let you do another kind of metaprogramming based on interfaces and creating generic code which you can plug together like Lego bricks. Okay, so to me this is the more interesting version than macros. I'm not going to teach you how to write macros, but I am going to teach you how to use multiple dispatch, right? Because it's the real thing that gives you the power to create something that's kind of, yeah, like I said, pieces that glue together like Lego bricks, right? Like Paul would have spoken about like Unix programs, which are small and composable and they piece together and you can pipe them into each other. And so like you can do the same in programming languages. You just have to take a little bit of care about how you structure things so that they work together seamlessly without even having to know what people are planning to do with it in the future, right? So Julia will construct on demand a particular program specialized on whatever inputs you give. So you can like call generic functions that will actually go ahead. And if you're used to writing a language like C, it'll basically like create kind of in its head, it's sort of creating almost like a C program just for those data types you provided and then compiling that like it would in a C compiler. And that's how you get the speed in Julia. Okay. So like, you know, if you add 2 integers, you get, you know, the machine instruction for adding integers. If you add 2 floats, you get the machine instruction to add 2 floats, but it goes all the way up to bigger and bigger, more complicated functions and programs. You can sort of, it'll kind of compose together that way to compile. So we'll talk about types next, but first I want to talk about functions. So functions here at the heart of Julia, and they actually have some interesting sort of syntax around them as well. Okay, so what we can see is there's multiple ways of creating a function. They're all identical. They're all syntax sugar for one another. So there's this one, which is like a long form, like starts with a function keyword. It creates a code block. You have to write end at the end to end the code block. And it's like that. And then there's a short form, which can also be useful. Now, you use the short form. It looks a bit like mathematics, and you use that when you have a one-liner. And then you use this one when you need more than one line, okay? So that's just generally a rule. What you can do is you can really piss off your workmates by like using this form and writing a giant line, which goes over here, and it goes over and over and over and goes off the end of the screen, and they have to scroll across, and it's impossible to read, right? But friends don't do that to friends, okay? What you want to do is you want to like split your code over multiple lines so it's nice and easy to read what's going on. But of course, if all you have to write is little things like that, it's also annoying to clutter up your code with 3 lines when it's more concise to write it in one, or more easy to understand like this form probably. Okay. There's a third one. These are these arrow functions or anonymous functions. So this form is pretty much exactly like the others. I've got a const here. Don't have to worry about why that's there. Particularly, we'll go into scoping a bit later. But basically, this lets us, like these things, create named functions. So this const def3, this means we're actually taking this function and giving it a name. And we can do things like find the type of that name and attach methods to it in the future, do different things, just like we can with F2 and F1. Okay. And then I've called this an anonymous function. Like it doesn't have a name. There's nowhere there it says that it's called F. Like it does over here, but I didn't have to write that left-hand side of the equals, right? I could create a function without a name, but I could also create a function without a name in the short form. So to do that, I just sort of delete those two characters there and have this thing. Again, yeah. So that's 4 ways of writing functions. They're all identical. I'm still going to show you another few after this. Okay. So Julia's all about functions and methods and types. And so they've sort of allowed a lot of rich, complex ways of writing these things. But I just want you to, when you're going forward, like you can recognize that it's just a function. Like, there's nothing fancy or special. It's just another way of writing a function. Now, the most interesting kind of functions to me are closures. Okay, so these are function which are created by function and returned. Okay, so remember this syntax here is just a function syntax, right? So I can have a function called adder. So it creates an adder for me. That's maybe I should call it make adder or something like that. And it returns this thing. Okay. So this thing itself is a function which takes one input, which is just called y here. The name doesn't really matter, and adds x to it. And x is the input here. So, okay. So I can create this thing, this object called add2 by making adder of 2. So what does add2 do? Well, it adds 2 to things. Okay. So it's right there in the name. So if you use add2 itself is a function that takes one argument. If you call it, you get another function back. A number back. 3 plus 2 is 5. Okay, we can do maths. Yeah. How does that work? How does this actually work? Well, actually, this doesn't actually introduce any new language features at all. This is just syntax sugar. Okay, so if we look at add2, it's actually storing x inside it, like it was a struct with a variable x, like a field x in it with the value 2. Okay. And that way I can take this add2 and I can pass it to other functions. I can even go so far as like serialize it and send it to another computer running Julia with the same code and deserialize it and get it out and run it over there, right? Yeah. So this thing is sort of like a struct. Like I said before, this arrow syntax is just a short, concise way of writing functions. So it's actually, and you'll see this a fair bit in Julia, is you actually see function keywords like nested inside functions like that. But that's just syntax for the same thing. You could give it a name or not give it a name. It's really up to you. But this is 100% identical to the previous one. Now, I haven't given a name, so Julia makes a name up for me, and it makes this name. So the name actually is this with the hashes. So what does hash mean in Julia again? Like a comment, right? So hash is a comment. So if I want to do something like this at the command line, I'll go like hash x equals 2. Well, what's that done? What's that done? Some bugger all, right? Like, because the parser would just ignore the entire line. Everything after the hash is ignored. So it's almost impossible for someone to write a variable like that. So it's creating a variable name which a user would never enter because it starts with a hash. But internally, the compiler just cares about strings. It doesn't care what the hash is. So internally, it's a symbol. So a symbol is a string. The compiler's put in a little dictionary somewhere in its memory and says, okay, I know this string. I've seen it elsewhere. And the way you can sort of create that is you can create for example, the symbol like this. Yeah. So there's a symbol constructor. So normally, like, you can create a symbol X like that, right? But that's the same as that. But this longer way of writing it lets you construct symbols you wouldn't normally be able to do with the surface syntax. You can put spaces in it like that, for example. Yeah. And then there was this thing, this var thing, which is itself a kind of a string macro. You can kind of actually, here's a fun one. So equals 42. And then I can get that variable. So you can actually kind of write code using things you're not meant to write code with. So for example, I've had structs, for example, with the word function in them, right? And they've come through to me from other programming languages in JSON. I've just deserialized them into structs. And so I've had to use like this before so that I could actually sort of refer to that thing as a variable and so on, just to kind of, it's something that happens. Okay. Now this thing, it's given a random name. It has this thing here. So this is a type parameter. So I said this is a syntax transformation. This doesn't actually know the type of what X is. So they've made a generic type and a parameterized type. And so in this particular instance of add2, it knows that X is an int64, right? And it's also attached a method to it. So there's one method and it's the thing defined here, right? And that's what that's telling me. And so basically I could have written this thing here with this equivalent code. I could have created a struct and given it a more sensible name, not like that silly name like before. We could give it a generic type T. We could create an adder. Like we could define like a constructor or like, sorry, a method. Sorry, this is a method. So here we're taking adder. So the thing on the left is the function. So long as A is any type of adder, then there's a method here for that. And this adds a.x to y. And this function that I meant to find before just constructs one of these structs, which happens to have this method attached. And that constructs this thing and it behaves the same way. I can call it with 3 and get 5. Okay. So closures are just syntax sugar, right? So don't be scared about them. Use them at will. But yeah, they're really important when you're using higher order functions like map and filter and things like that. So here we're starting to talk about types. So probably the most important bit of syntax around types is a type assertion. So here, you can just use the type assertion operator anywhere, right? It's a sort of expression. You can put it anywhere in your code. It's perfectly valid. And what that means anywhere in your code is it's an assertion that the thing on the left has the type on the right. Okay. So, and when it's finished, it just returns the value. So it just discards. So what it does, what it's actually doing, is it checks the type assertion. If the type is correct, it just returns the value. If the type's incorrect, it throws an exception. Okay. So here, for example, 42 string, 42 is not a string, so it throws an exception. Now, Julia has like an abstract number type, which is like a super type of int, but it's also a super type of float and other things. And so that also passes that assertion, right? That type assertion. And this is fine because int is a subtype number. And so this is another operator in Julia. It takes an expression. This expression type always is a Boolean, right? So it returns true or false. And so you can use this in your code. You can use this in various places in Julia. So, and then there's this type called any. So everything is type any. It's a super type of everything, right? Whenever you create a type, it's always a subtype of any. It's just a rule. So this more or less is what you call a no-op, or no operation. It doesn't do anything. Okay. So when computers were slow and physical, like that often have like spinning drums and all sorts of things, you couldn't like fire off instructions on the CPU necessarily one after each other really quick. Sometimes you'd have to add no-ops and the CPU would wait one tick and wait maybe another tick, and then maybe you can do the next operation. Because, you know, the electronics that, you know, they're not ready yet. They're still excited, or, you know, you've got to wait. In the case of the drum memory, wait for the memory to come back around or whatever it is. So that's an interesting thing. So, but you got to think x and x dot dot any is sort of always the same thing, always. So when we define a function, okay, so when we define a function, we can use this in a slightly different way. So it kind of means the same thing. In this statement, it's always true that x is an int. If you're executing this code, if you're called f, and you're executing this code in the right, you can trust this type assertion. It's definitely true, right? Otherwise, you wouldn't get here. It would error out. It would go to another method. So it's still like a type assertion that doesn't do anything because it's true. But it also defines sort of the argument types that this method acts upon for f. Okay, which is fine. And then you could have another one for number, and you could have like another one. And this is the syntax we're using before without a type assertion. Now, just remember, I said x and x any is exactly the same thing. So actually, it's probably best to think of this function with colon any here, and it's a method. All right. So if I type this in at the REPL, that doesn't. They've shortened the form in 211.7. Sorry about that. But what it should probably say is that this is a colon any. What it used to say. Now, in a sense, the third method, in some way, it's not safe, right? I could put in anything in there. What would happen if I put a string in there? And try it. Let's try it. It's going to go. Well, actually, multiplication of string is defined to be concatenation, and squared reduces to, timesing two things together. So it actually just works. But there are other things, like I could call it with a tuple, and it would error out, and sort of say, okay, I'm in this method, right? I'm in the f method. I'm trying to do this power thing that it has, but it's screwing up because I can't like do a power of that. I can't take the power. I can't multiply tuples. And there are lots. I couldn't multiply symbols. I couldn't multiply files. There's lots of things you can't multiply, right? But on the other hand, it might be a little less safe, but it's also the most flexible, right? Someone come along with some new data type I haven't thought about and run it in F, and it'll be fine. Okay, so what we're going to try and get to on next Monday is my goal will be to try and teach you a way by the end of it, right? Because we've got a bit more content. Teach you a way to write functions which are both flexible, but also people can come around later on with their new types and then with their own behavior that you don't even think about, and you can put it in your function and it'll work fine. Okay, and that uses something called interfaces and traits and things. And we'll touch on that, and we'll try and get there, but So I've got like 3 minutes. I'll just talk about a couple other bits and pieces with functions, and then we'll stop, okay? So varargs, so some functions have a variable number of arguments. This is shortened to varargs commonly, or variadic functions, another way of describing them. So Julie has this ... thing, and it's sort of like, it means sort of like slurp up everything and put it in here, okay, in this case. And it also has the same ... notation, which means splat it all out and stick it over there. And you can't actually tell which is which. Like the designer of Julia was like, I wish I put one on the left and one on the right, so you could actually tell. But in this case, this is like collecting everything that's coming into the function and putting it into input. By convention, the compiler makes a tuple for you, not a vector or something. It's actually a tuple. But tuples are still sort of iterable, and you could write a function like add all the things, and like it starts with 0 and it takes all the inputs and just adds them to out and returns out. So it sort of like sums everything up. So like 1 + 2 + 3 + 4 + 5 is 15, right? And that just works. And so like maybe you're a mathematician, you're interested in polynomials, and maybe you're doing unit 5 and you're interested in polynomials, nudge, nudge. You might create functions like this where, given some parameters A, which are like coefficients of a polynomial, they're meant to be interpreted as, we're actually going to create another function, the polynomial itself, which sums up, those coefficients of A times like x to some power, right? Where the power is from 0 to n, and n is like the length minus 1, right? So maybe you could do like a quadratic function. So this would be like 1 + 3x minus 10x², right? And we could create this polynomial. This is a function, right? Remember, this is a function that returns a function. It's a closure. So we could evaluate this at a few points. And you can sort of see it's positive around 0. and it's negative at -1, it's negative at +1. So who knows where this function crosses 0? It must cross 0 somewhere in between, right? So where are those points? Okay, so we just created this closure. It's like just some new thing we invented on the spot. We're going to download this roots package, the roots of polynomials, that's sort of roots, and use the function in roots called find zeros with our polynomial. And we're going to say, okay, start looking at between -10 and 10, just limit your search to there, and it'll actually come up with the answers for us. I suspect this is really meant to be -0.2, but yeah. That I think gives you a little taste of like how in Julia you can like just create stuff and throw them into other things and they just sort of work out, right? And like the interface find zeros cared about is that the polynomial is just something you can call with numbers, right? And it could be anything you can call with numbers, right? And so this is what I mean by interface. In Julia, the interfaces are informal. You document them in English or your native language, and say, oh, the first argument needs to be a function which takes a number and returns a number, right? And it has to be, we assume it's going to be, say, smooth or continuous or something, right? And therefore, based on that, we'll be able to find the zeros. That function will find the zeros. It's 5 to 7. We've got a little bit more syntax to run through on Monday. A couple more little bits and bobs about functions, but again, it's just a little bit of syntax, just so you know what you're looking at. And then we'll talk about how types work and how to define methods, what methods are, what is multiple dispatch. And then I'll get more into like how you use that powerfully, how you organize your code into modules. And possibly we may end up with a little bit of like the package manager and like how to actually go ahead and use Julia and Git and all those things nicely together. So, and the idea is just to give you a foundation to do your project 1 and project 2 and project 3, where you're going to have to build larger software, not just like single liners. It's going to be a program, not a huge program, but a somewhat complex program in its own right. Yeah. Are there any questions before we head off? Anyone? Oh, here we go. Type of @h doesn't return anything at all. So type of @h. I'm not sure if that's just because of the is a comment or because, but basically function, everything has a type, right? So f was a function. You can get the type of a function, right? And you can get the type of that. Everything has a type. And the sort of fundamental type in Julia is data type. And I'm going to cover data type on Monday. All right. Thank you, everyone. Sorry, say it again. Yes. Yeah, that's what I mean. That's sort of the end of the train, end of the line. Yeah. So data type is itself a data type. Again, it's very meta. But I have to go to Zoom, I have to go here, right?